Page 130, section 2.8 is on proportions and similar figures. So we've already talked about proportions. We're going to talk about how that relates with similar figures and finding missing measurements. In similar figures, corresponding sides are proportional and corresponding angles are congruent. So kind of like the sides that match up with each other, they have the same proportion or the same way of getting from one to another, like maybe one's 2 times as big on the other one, something like that. And then corresponding angles are congruent. So if the angles are in the same spots, they have the same angle measure. So like if one is 30 degrees, the one that matches up with it will also be 30 degrees. Kind of the idea with similar figures, if you've ever done something on Microsoft Word or a program like that, if you've inserted an image and then if you drag the corner, you can make something bigger or smaller proportionally. Okay, not taking it from the top or bottom or left or right, which just stretches it, but if you take it from the corner, you'll get a similar figure. So if we look at this, for example, on this triangle, these triangles are similar. There is a symbol that's used, looks like a little squiggly line, which means similar to. So in this example, we've got triangle ABC is similar to triangle FGH. So one thing you'll notice is with the side lengths. Well, before we do that, let me just mention the order that you do your similarity statement in matters. So if I do this, triangle ABC is similar to triangle FGH. What I'm saying, A and F are in the same spot. So I'm saying angle A is congruent to angle F. B and G are in the same spots. So I'm saying angle B is congruent to angle G. C and H are in the same spot. So I'm saying angle C is congruent to angle H. And then also I'm saying that these ratios are the same. AB is the first 2 letters, matches up with FG, first 2 letters. AC is the first and last letters, matches with FH, first and last letters. And then BC, last 2 letters, matches with GH, last 2 letters. So those proportions or ratios are going to be the same as each other. So if you look at this picture, then we can see that. So AB and FG, how do I get from AB to FG? Multiply by 1.5. So in other words, if you do 12 divided by 8, you'll get 1.5. So we're multiplying by 1.5. 10 to 15 multiplied by 1.5. 12 to 18 multiplied by 1.5. Or I didn't write it this way, but basically if these were fractions like 8/12 and 10/15 and 12/18, as long as we don't have any decimals in these, if there's no decimals in these, then they should all reduce to the same fraction. So these all reduce to 2/3. So one of the triangles, the smaller one, is 2/3 the size of the bigger one, for example. So if we look at problem 1, triangle ABC is similar to triangle DEF. What is DE? So DE is what we're trying to find. We want to see what that matches up with. DE, if you look in the similarity statement, that's the first 2 letters. So that should match up with AB in the other triangle. You might just think, oh, I can just look at the picture and tell what it is. Sometimes figures get flipped or rotated, reflected, rotated, stuff like that. So we can't always just say, I'm going to look on the picture and tell. We always want to look at that similarity statement to double check that. So in this case, DE does match up with AB. And so what we could do then is we could do a proportion. When we do these a little different than the book, I like to start with what I'm trying to find. So if I say X, so the X matches up with 10. X was from the smaller triangle, or the triangle on the right, if you want. We want to call these right and left. If you have a hard time with your right and left, maybe big and small would be a better one, or you could even color them in if you'd like. Call them the blue triangle and the red triangle. Anyway, this X was from the right triangle. Our numerator in the second fraction has to be also from that triangle. What we need to do is look at what numbers we know in both triangles. So like at the bottom, here's an 18. I don't know what this other dimension is though. So I'm gonna have to go to this other spot. So I know a 12 and a 16. 12 is gonna go across from the X, because it's from the same triangle, and then that would be over 16. Potentially we could reduce, we could find patterns here. If not, we could say they're dividing by 10. I'm going to multiply by 10. And then when you divide that out, you'll get 7 5/10 or 7 1/2. They didn't tell us what the units are, so we're just going to leave it at that. So same idea if you look at the got at 1. So the got at 1, they want us to find what AC is. So it's the same idea. AC is at the bottom here. I'll just call it A, I guess. So the A matches up with, on the other triangle, 18. And then let's go back to what we know was this set here. So A matches up with 18, just like 16 matches up with 12. We could use the answer we just found, but if that's wrong, then we're going to be wrong on this problem also. And again, if you wanted to, you could just say that it's being divided by 18. I can multiply by 18. Again, if you want to look for patterns, or if you want to cross multiply, that'll work also. Anyway, you work this out and you should get 24. The next part of the book talks about how we could actually use this ourselves, and what's called indirect measurement. So indirect measurement is we're finding lengths we can't measure directly. So if I'm trying to figure out how tall this building is, unless I can get on top of the building with the big tape measure or something, I'm going to have a hard time to measure this building. What I can do though is I can do indirect measurement, and this sometimes, what they're doing in this problem, they sometimes call shadow reckoning. What that means is at a certain point in the day, if it's sunny outside, what we can do is measure how tall we are or some other object and the shadow, and then measure the shadow of the object we're trying to find the height of, and then we could use, these are similar triangles, we can figure out the height of that building. So on this problem, I would start out differently than the book, but if we draw the picture here, what I would say is X is what I'm trying to find, matches up with the 5 feet height, and then X is from the big triangle, so we need to put from the big triangle would be the 15 feet on top, matches up with the 3 foot shadow. Now it's not a big deal in this problem. I've got a nice pattern here, so it really doesn't matter. And if you just want to cross multiply every time, then the way the book did it is fine. But like I said, I like this just because then if there's not a pattern, I can say they're dividing by 5, I'm going to multiply by 5. Okay, and what we can see here is that this is multiplying by 5. and so that would be 25 feet tall. You might be able to look at it also. If it doesn't specifically say you have to set up a proportion, you might just say, the shadow of one is 5 times as much as the other one, so the height's going to be 5 times as much. That would be another way of looking at it.
15 by 3.
So look at the got it 2. When you're doing these, what I would suggest is that we draw a picture out. You will not be judged by your picture. Just like don't judge me for my picture. A man who is 6 feet tall is standing next to a flagpole. Shadow of the man is 3.5 feet. Shadow of the flagpole is 17.5 feet. What is the height of the flagpole? Okay, so we're going to draw this out. So we have 6 feet. And that person's shadow is 3.5 feet. Okay, this is not to scale because that 3.5 looks like more than the 6, but we just got to trust the picture, trust the numbers. Okay, and then we have a flagpole. And we're trying to figure out the height of the flagpole. We can make that into a triangle with its shadow is 17.5 feet. So if we draw that out, these are similar triangles, then we can figure out what the height of the flagpole is. So if we were going to set up a proportion here, if you want to start with the H matches up with the 6 feet on the other one, and then we'll go with the same order. One way to keep track of this, if you want, you can say H is from the big triangle, 6 is from the small triangle, then we make sure we do it the same on our second fraction. So it'll be 17.5 over 3.5. And again, we can find a pattern here if you want. So 17.5 divided by 3.5 is 5. So this going towards the variable would be multiplying by 5, and 6 times 5 is 30. So 30 feet. Again, you could also just multiply by 6 on both sides, or you can cross multiply if you want. And like I said, if you somehow can show me otherwise, and if you can show me somehow and it doesn't say you have to write a proportion, then you can get by with that also. So the next thing in the book talks about scale drawings. Scale drawings can be used when we want to make either a smaller or bigger drawing of something. A lot of times we do smaller drawings to make it more practical, like blueprints of buildings or maps. Sometimes it might be something we want to make it bigger so we can see it better. For example, I used to have a poster of a calculator, and it had a big poster of the calculator, and then that way I could point out buttons on the calculator more easily. Or like in science, things are really small sometimes. They might have something enlarged so you can see it better. So problem 3, we're looking on the map here. What's the actual distance from Jacksonville to Orlando? Use the ruler to measure the distance on the map below. Okay. And some of this stuff, you might look at it, you might say, well, I could just go on the computer and find the directions and it'll tell me exactly on roads how far it is, instead of just, I know I can't go directly between these. This is what they used to have to do, okay? You can probably talk to your grandparents about it, or maybe your parents. So anyway, on this problem, the map scale is equal to the map distance over the actual distance. So here's our scale. And what we can do is, on the map, how they've measured this, they're saying that's 1 1/4 inches or 1.25 inches. On these, I usually just do these the way the book does, just seems easier. So 1 inch is 110 miles. We have 1.25 inches is equal to something. I like to put the units so I make sure I'm putting stuff in the right spots. The good thing about these is usually when they give you a scale, it's like 1 inch equals this, or 1 centimeter equals this. If there's a 1, I have a pattern every time. So no way I'm gonna mess with cross multiplying. 1 times 1.25 is 1.25. So then if we just do 110 times 1.25, and then we'll get our answer. Now this one wasn't as big of a deal then with the 1 being there, because 1x is the same as x. So 137.5 miles would be the distance there. So if you look at the guide at 3, distance from Jacksonville to Gainesville is about 6/10 of an inch. What's the actual distance? Same thing. We could just start out with the scale they gave us. So 1 inch is 110 miles. And we've got 6/10 of an inch is something. Okay, again, every time there's a pattern. So that would come out then as 66 miles. And again, just kind of make sure when you get your answer, think about if it makes sense or not. It's about 1/2 an inch, a little over 1/2 an inch. Half of 110 is 55, so we should be okay with that answer. So if we look at the bottom of the page, talks about scale models are 3-dimensional models, similar to the 3-dimensional object. And it's kind of the same idea as what we just did with the scale drawings. So problem 4, a giant model heart is shown below. The heart is the ideal size for a person who is 170 feet tall. About what size would you expect the heart of a man who is 6 feet tall to be? Okay, so the deal is 14 feet for something. And again, I would start with what I'm trying to find. I would say X is the heart height compared to 14 feet. And then this is our regular person, I guess. Regular person is 6 feet tall. The model is for 170 feet tall. And then we could figure this out. Again, if I set it up this way, I can just multiply by 14 on both sides and then divide it out. Understanding this is going to be in feet. So just roughly, it's about 49 hundredths of a foot, so about 1/2 of a foot. We could multiply it by 12, you know, just a little under 6 inches, we could say. So if we look at the guide at 4, again, if you want to start with the scale, you can. 1 inch is 50 feet. So the scale model of the building is 6 inches tall. How tall is the actual building? So check your units out here, and the 6 inches then would have to go on the top. I've got a nice pattern here. It is multiplying by 6. So this would be 300, which means 300 feet. So the lesson check number 1, use a photocopier to enlarge a drawing of a right triangle with a base of 13 centimeters and a height of 7 centimeters. The enlarged triangle has a height of 17.5 centimeters. So they're asking what the base is and what the scale is. So if you want to, you can draw a picture here. So base is 13 centimeters, height is 7 centimeters. Enlarged triangle, not to scale necessarily. Height is 17.5 centimeters, and we're trying to find what the base is. So if you want to call that B for base, just make sure it doesn't look like a 6. So the base matches up with 13. just like 17.5 matches up with 7. And again, if you wanted to, you could just say they're dividing by 13, multiply by 13. And then when you work that out, you should get 32.5 centimeters. So that's for the base. The second question is, what is the scale of the enlargement? When we talk about scale, what we want to do is we want to do the model over the actual, or the model over the original, however you want to say that. So in this case, if we look at what we knew, the model, in the model, it was 17.5. The actual that matched up with that was 7 for the heights. 17.5 on the model matched up with 7 for the original. When we do a scale, it's nice to have a 1. So if you divide those both by 7, we'll get 2.5 over 1. So we could say 2.5 to 1 is our scale. Which basically just means the one is 2.5 times bigger than the other one. If we look at number 4, they want us to tell whether these are equal. So this just goes to our similarity statement. So angle A and angle T, would those be the same? Well, A is the first letter and T is the first letter, so I would say yes. Perimeters of the two triangles. Well, if they're similar, they're not necessarily the same size. They're similar. Proportional, but not the same size necessarily, so they would probably have different perimeters. And then these ratios of sides. So BC to UV, second, third, and AC, first and third, over TV, first and third. And also notice this was from the one on the left, this was from the one on the right, this was from the one on the left, this was from the one on the right. So that works. Those ratios would be equivalent. So this gives you an idea of how to work with proportions and similar figures.